Hey guys, I'm here back with another math video. Today we're going to be proving an interesting property. So given any volume that tapers to a point with any shape with an arbitrary base of any size or shape, given the height of h naught, the volume of the shape will always be the area of the base times the height times 1/3. And this 1/3 seems completely arbitrary. Don't know where it comes from. We know that the volume of a cone is always 1/3 of the base times height, which is like the volume of the prism that it fits into, right? It's always 1/3. So is a square pyramid. It always fits. It's always base times height. It's still 1/3, and it takes up 1/3 of the volume of the square prism that it's like inscribed into, right? And it seems like really arbitrary. Like, why would the volume of a cone be 1/3 of the prism that it's inscribed in, or why would a square pyramid or a tetrahedron always be 1/3? We're going to prove that today using integration. Now, when we integrate a shape, what happens is that when we want to find the volume of this using integration, we want to find the sum of all these cross-sectional areas as the height let's say we choose a point along h naught, which is like right here, and let's say h is denoted by this length. We want to add up all these cross-sectional areas that are parallel to the base as we approach the tip, right? We want to add up all these tiny slivers of volume. We want to add up all these cross-sectional areas as we approach the tip of the volume. If you don't know what I'm talking about, you should watch one of our videos on integration, or learn a bit more about integration, because I'm not going to explain it all in this video. But basically, in integration, when you try to integrate to find a volume, essentially you're trying to add up all the tiny slivers of volume that these cross-sectional areas parallel to the base make up. To do that, given an h, we have to find the area of the cross-sectional area parallel to the base that h represents. So given an h, what is the area of this, given that the area of the base is b? What's the area of this cross-sectional area? And to figure that out, we need to know some properties about similarities. So given two volumes that are similar, say this is a tetrahedron and you have a bigger tetrahedron, and this tetrahedron has length a, and this tetrahedron is length a, and this tetrahedron is length 2a. So the lengths will all be doubled, right? The lengths of this similar shape will all be doubled. However, the surface areas in two-dimensional values, like the area of this face or the surface area of this, will be quadrupled. It's this factor squared. So the area of this will be 4a. Well, 4a. It will be multiplied by a factor. So this is a, like the area of the face. This is 4a, and the volume will be cubed. So volume of this is this cube. So if the volume of this is like VA, this is like 8VA. So lengths are doubled. Areas are quadrupled, and volume is multiplied by a factor of 8, because with one-dimensional areas, it's just the factor. With two-dimensional areas, you multiply by the factor squared, and three-dimensional areas, you multiply by the factor cubed. So what's the factor here? Because we know that these two shapes are similar, right? Because this volume is inscribed in this volume. So given an h, we know that the factor being multiplied is h over h0. That's basically the factor that the lengths in this volume is being multiplied by. So did you know that the height is decreased by a factor of h over h0? So the area of the base is multiplied by a factor of this squared, because the area is a two-dimensional a two-dimensional value for the volume, and those are squared, like, right? Because like this face is like a and this is like 4a. It's a factor squared. And we so that's the factor that b is multiplied by. We multiply that by b to find equals cross-sectional area. And to add up all these slivers of cross-sectional area, we use an integral. So h goes from 0 all the way to h naught. It goes all the way down to h naught. And we add up each of these cross-sectional areas, right? Add them all up. And that function is h over h0 squared times b. And the integral will tell us what the sum of these values are. Sorry if you don't really get that. I feel like it'd make more sense if you guys know what integration is, and if you know basic properties of similarity between three-dimensional figures. I feel like that would be really clear. I'm trying to like really poorly explain it to people who don't understand those concepts, but I think if you have a grasp of these concepts already, it's way simpler. Alright, let's take the integral of this. So this, since h is the value we're taking the integral of, we're going to rewrite this to be b over h0 squared times h squared dh, which is equal to 1/3 times b over h0 squared times h cubed from 0 to h0, which means that it's 1/3 b h0 minus 1/3 b over h0 squared times 0. This becomes 0. So the volume is 1/3 b h naught, which is the same as that. So we sort of proved it. So what we proved basically is like given any shape, given a base of any shape, and if you want that shape to taper to a point, the volume is always going to be the area of the base times height times 1/3. It doesn't only apply if the base is square, if the base is circular, any shape base. So I think that's interesting. I mean, it's a pretty simplistic proof if you know some calculus. And I think it's cool how calculus can also apply to like geometry and stuff. Thanks for watching. So by this logic, you can actually generalize this. So the intersection between, the union between A, B, C, ... to like X would be